So yesterday we were discussing something called as double Dirac Delta potential, and today we'll take on with this problem itself. So yesterday we were doing, in the last section that we were doing was that if a particle of mass m, if a particle of mass m is subjected to a double Dirac Delta potential, to a double Dirac Delta potential. So if it is subjected to a double Dirac Delta potential, and I gave this potential in a manner that the Dirac function is located at, I think, x equals to plus a and x equals to minus a. Okay, so I think that was the case that we were doing, and we were considering the bound states only. Like we wanted to find the number of bound state possible. So we wanted to find the number of bound state possible at the later on, and initially we were interested, and we actually derived wave functions. So wave functions of the bound states following the above given potential. So if your particle follows, if it follows the above given potential, then what will be the wave function of the bound state? What will be the wave function of the bound state? This is something that you have to do. Okay, so how to go about it? Let us see. So yesterday I almost derived it, but again I'm going to derive it all over again today, so that it suits you. So initially we were trying to, whenever we have to solve this Dirac Delta function, so what we do, we actually write the Schrodinger equation. So the Schrodinger equation, I'm writing it now in one step, that is d square psi upon dx square plus 2m upon h kt square. And then we had, I think, some v naught Dirac of x plus a, and then we had some Dirac of x minus a, and then we had plus 2me upon h kt square psi of x equals to 0. Here also sub psi of x. Okay, so this was it. Now, but whenever we are supposed to find, whenever we are supposed to do the integration, which whenever we are supposed to find the solutions of the wave functions, when we are discussing some Dirac Delta potential, what we do, we actually start with a condition that Dirac says that x should not be equals to plus minus a. Here in this case, x should not be plus minus, because if x is equals to minus a, or if x equals to a, then this will become infinite, and it will be difficult for us to extract the wave function. So what we do, we take the case that x should not be equal to plus minus a, then Dirac of x plus minus a would be 0, and we can go along. And already we know that energy is negative, so energy can be written as minus of modulus of p, and all those things will give us Dirac d square psi upon dx square minus k square psi equal to 0, where your k square is equals to minus 2me modulus upon h ket square. So this is how it is. Okay, now, sorry, k square is 2me modulus 1 h ket square. Now we know that the solutions to this differential equation can be of this type, that is either it can be e to the power kx, or it can be e to the power minus kx. Now what to do? Now this depends upon what are our conditions. So for example, we already know that we are discussing a Dirac Delta potential. So Dirac Delta potential means we have Dirac Delta potential, double Dirac Delta potential located at x equals to minus n and x equals to a. So now there are three cases. That is, one case will be x less than minus, one case will be x lies between a and minus a, and one case will be x greater than a. So it is clearly, you can clearly see that for all x greater than a, e to the power kx cannot be there. So only function that can remain is e to the power minus kx, because e to the power kx would blow up to infinity as x tends to infinity. Similarly, here we can only have e to the power kx, and here we can have both e to the power kx plus e to the power minus kx, or e की power kx minus e की power minus x. Both of these wave functions are possible. We'll multiply it with some suitable arbitrary constant. Don't worry about it. But most possibly, we can have both of these combinations. Okay. Now, there is a theorem in quantum mechanics that we'll study in operator theory also. We'll do all these things in operator theory. That if potential is symmetric, that is, if v of minus x can be written as v of x, then the wave functions have a definite parity. If the wave functions have a definite parity, that is, either they are odd or they are even. So, I can write wave function will either be even or odd. That implies that your wave function can either be written in the linear combination of even wave functions, or wave function can be written in the linear combination of odd wave functions. So their eigenstate would either be entirely even or their eigenstate would entirely be odd. So we yesterday formulated this thing. So that is what I'm doing. So yesterday when I was teaching you this, I was saying that psi of even can be written as, let's say, for all x greater than a, I can write a e की power minus kx. For all x less than minus a, I can write it as, I think, a e की power kx. And for all x lying between minus a and plus a, I will use this expression e की power kx plus e की power minus kx, because this is an even function. So I'll use a b up before it, and this entire thing can be written as cos hyperbolic kx. Similarly, psi odd can be written as a e की power minus kx for all x greater than a. For all x lying between minus a and plus a, I can write sine hyperbolic kx. X lies between minus a and a. And for all x greater than a, I can write it as minus of a e की power kx. Why I should write a minus? Because if I don't write a minus, then psi odd minus x will not be equal to psi odd x. So in order to satisfy this condition, that psi odd minus x should be minus psi odd x, that to fulfill this condition, we place a negative there. So this is how my wave function would be constructed. Okay. In examinations or otherwise, you may be asked, or you may think, what sort of wave function would look like. I mean, how this wave function would look like. So understand my point. I'll make okay. So what I would do is, so what I would do is, first I'll try to make a graph of cos hyperbolic x. So how does cos hyperbolic x look like? So for example, cos hyperbolic x is represented by linear combination of e की power kx, which is this, and then e की power minus kx, e की power minus kx, which is this. So this is how your cos hyperbolic, this is how your e की power minus kx and e की power kx lies. This is e की power minus kx, this is e की power kx. So if you want to make a sum of all these things, so basically sum will lie somewhere in between. Sum will lie somewhere in between. At x equal to 0, it is equals to 1, and then all over again. So this is how you will write your function, that is cos hyperbolic x. So this is how your function cos hyperbolic kx looks like. So cos hyperbolic x looks like this way. I've made this graph. Again, I'll make it all over. So this is how your cos hyperbolic x look like. Okay. So this is how your cos hyperbolic x looks like. Okay. Now, if I'm supposed to make the plot of this, for example, if someone asks you how does this particular wave function look like? So, I mean, how can you graphically represent this wave function? So this would be one of the most appropriate answers to it. Okay. So now, for all x less than minus a, your wave function is like, for all x less than minus a, your wave function looks like e की power kx. So you just trace the graph of e की power kx. So till now, your function would be like e की power kx. Then after this, your function looks like cos hyperbolic x. So had this cos hyperbolic x been drawn, so entirely this way, cos hyperbolic x would have been there. So, but for example, if I have to draw cos hyperbolic x, it would have started from here, there, and this way. But now you just have this. This will look like this. This is your cos hyperbolic x. And after x greater than a, again, your function would behave as if it is e power minus kx. So this is how I can plot your. Is that clear to you? Bharat, समझ में आया? So if I'm writing my psi e1 as a function of x, then this is your e की power minus, sorry, this is your e की power kx. I'm not writing a constant, forget about it. This is somewhat graph of e की power kx, and this is somewhat graph of cos hyperbolic kx. Is that clear to you? Now, instead, if I make the graph of, let's say, now how to make the graph of sine hyperbolic x? For example, if I have to make the graph of sine hyperbolic x, what I would do is, okay, if I have to make the graph of sine hyperbolic x, what I would do is, I would simply make a graph of e की power kx. So here it is, e की power kx is here. You can make e की power kx this way. How would you make e की power minus kx? E की power minus kx would be this way. Okay. थोड़ा सा I mean थोड़ा ज्यादा स्टीपर बनाना चाहिए, तो फिर कोई बात नहीं. This is how e की power minus kx is there. Now, if e की power minus kx is this is e की power kx. But now what we want to find is sine hyperbolic x is e की power kx minus e की power minus kx. You just take a negative of it. So this is your negative. This is e की power minus kx minus. Now you just add these two up. So this is one, I'm writing one, this is two. Add one and two. So what will happen? If you add them up, what will happen? It will start this way. At x equal to 0, you can find that your sine hyperbolic x is 0. That will go on. So this is how your sine hyperbolic would be looking like. So this is your sine hyperbolic x. This is how your sine hyperbolic looks like. Okay, so this is how your sine hyperbolic x could look like. Now, I have to construct an odd wave function. Okay, so odd wave function was this. Just look at it first. This was how your odd function should look. Odd wave function should look like. So for all x greater than a, for all x greater than a, e की power minus kx. For all x less than minus, my mistake. For all x less than minus a, my wave function should be minus a e की power kx. This is how my wave function should be, right? Is that clear? Now, if I make this plot, so for example, now let us make the plot of the psi odd. Let us make the plot of psi odd. So how psi odd would look like? So beyond a, my wave function is beyond a, my wave function is almost like e की power minus kx. So how does e की power minus kx? Had e की power minus kx would have been here, so it would have been like this only, ना? E की power minus kx ऐसे चल रहा होता, but we have to just plot it beyond x equal to 8. So beyond x equal to 8, this is your e की power minus kx. Okay. Now, in between minus a and a, there is a sine hyperbolic. So I'll make a sine hyperbolic graph. Okay, sine hyperbolic would look like so not certainly like this, but support. Okay, so this is how your sine hyperbolic would look like. So it will go here, come to 0, then it will come to this place, and then it will rise up. and there will be a cusp here. Don't worry about it. So this is a cusp. This is a point where your wave function is non-differentiable. Okay, and that should be the case. We already know that that at x equals to plus minus, we had a Dirac Delta function. So always, I'll again reiterate the same to you today again. Or in the I'll write it here itself. First we'll do it. So and for all x less than minus a, my function is, for all x less than minus a, my wave function is e की power kx का inverse. मतलब negative आगे लगे, sorry. So e की power kx, how does e की power kx behave? So e की power kx is this, but now you have to take inverse. So basically, you have to take a negative. So what will happen? It will start. It will become. We have to make a graph taking this particular axis as the mirror. So taking this particular axis as a mirror, e की power kx will be mirrored, because we have to plot the graph of minus e की power kx. So this is e की power kx. You have to plot a graph of minus e की power kx. So minus e की power kx would be, you just make an inverse. You just take a mirror image about of this particular wave function, that is e की power kx, about this x-axis. So how would things be? For example, here it is going towards, here it is going towards my 0, that is minus, as x tends to minus infinity, e की power kx goes towards 0, so it will remain 0, but on the negative. And then you have this. So this is how your psi odd wave function look like. So psi odd wave function as a function of x looks like this. So this is how we'll have this wave function. So it will be like this. There will be a cusp here. Then again, you can go on and see. Is that clear to you?
Yes, sir.
Okay. So this is how the wave function would look like. So these two are characteristic plot. At times in exam, because of the limit of the time, probably only up till this particular portion may be asked. Now, another thing that you should be seeing is in all of these Dirac Delta function questions. So we've made the wave function which we were interested in. Now I was reminded of a topic, so that is why I'm just writing. So whenever we were encountering a Dirac Delta potential, let's say for the simplest case, when we were doing it, that is minus V naught Dirac of x. So what did we do? We took the case x not equal to 0. We tried to write this way, minus k square psi equal to 0. All these things are done, so I'm not getting there, upon h cat k square. And what we did, we actually integrated. So when we were integrating, we were getting d psi upon dx on the positive end, minus d psi by dx on the negative end of 0. That is, we integrated this particular expression from minus epsilon to plus epsilon, and we already constructed psi of x is equals to some e की power, I think, kx minus kx if x is greater than 0, and for all x less than 0, it was e की power some kx, and there was a normalizing constant, let's say root over k. Okay, this is how it was. Okay, now you can see, while I was integrating all these things, so what I was getting was minus k square psi. Okay, not sorry. So not this expression we were integrating. We were integrating another expression that involved Dirac Delta function. So first step involved, we were not taking x equal to 0, we were taking x not equal to 0. From this, we obtained the wave functions. Okay. Now, after this, what we used to do was, we used to integrate our Schrodinger equation from minus epsilon to plus epsilon. So minus h cat square upon twice m d square psi upon dx square, and then we had some minus v naught Dirac of x psi of x, and then we had some is equals to e psi. Okay, and we used to integrate it. So when we are integrating it, what do we get? We get d square psi की जगह हो जाएगा d psi upon dx from minus epsilon to plus epsilon, and then plus v naught, and then you have this psi of 0, and then you have some 2m upon h cat square equal to 0. What did you find? You found by this particular thing that your first derivative d psi upon dx at x equals to epsilon minus d psi by dx at x equals to minus epsilon is some constant which is given by minus 2 mv naught x cat square psi naught. So this is some non-zero. So this is some non-zero value. When this is some non-zero value, what does it imply? It implies that your derivative, first derivative, is discontinuous at 0. So because this represents your right-hand derivative, this represents your left-hand derivative at 0. So this represents your left-hand derivative at 0. This represents your right-hand derivative at 0. And this is equal to some quantity. So basically, this represents the discontinuity in the derivative. So whenever you will find that your wave function is discontinuity derivative. Okay, so there is a discontinuity in the derivative. So you can see that there is a discontinuity in the derivative. And since there is a discontinuity in the derivative, and also you can see that second order differential equation is defined. So whenever you have the second order differential equation, what does it imply? It implies your first order derivative must be continuous. Because if a function is discontinuous, it cannot have a derivative at that point. But here in these cases, wherever you encounter such distributions called as Dirac Delta functions, what happens is your first derivative becomes discontinuous at some points. And despite being discontinuous, you have this second order differential equation. This is compulsory. I mean, this is your Schrodinger equation. So it cannot be wrong. So basically, your second order differential equation is defined. However, the lower order derivatives are discontinuous at some point. Such solutions are called as weak solutions. Such solutions are called as weak solutions. So there, in your main calculus lessons that you've learned till now, you always used to say कि अगर मेरी second order differential equation defined है, it implies your second order derivative is defined. And if second order derivative is defined, it can be defined only if your first order derivative is well defined. That is, your first order derivative must be continuous. But here you can see that your first order derivative is discontinuous. In fact, in the graph also you can see this was your wave function, and here it is a cusp. So what does it imply? At x equal to a, my wave function is non-differentiable. So x equal to a, my wave function is non-differentiable. Why? Because my left-hand derivative is not equal to my right-hand derivative. Therefore, I have encountered a cusp. Cusp is a double point. It is a point where your derivative is not continuous. Basically, wherever your derivative is not defined, we call those points as some double points or sometimes as cusp. So this is a cusp. This kind of you see this kind of structure is called as cusp in mathematics. So basically, what does it imply? It implies my derivative is not defined. Why my derivative is not defined? Because my derivative to the left and derivative to the right are not matching up. Okay, so till now, all these things have been done. So yesterday's only recapitulation I've done. Now, further we should apply some boundary conditions, and let us see the bound states. Okay. So now the main question is about bound states. So I'll write my wave functions at first and then we'll move ahead. So my wave function is psi odd. I'm writing here. My psi odd is given by, I think, a e की power kx if x is less than minus a. Minus a. And then I had for all x greater than a e की power minus kx. And then for all x lying between minus a and plus a, my odd wave function is, I think, b sine hyperbolic kx. And similarly, psi even, if I consider, psi even was, I think, a e की power kx for all x less than minus a. For all x greater than a, it was a e की power minus kx. And I think for all x lying between minus a and plus a, it was b cos hyperbolic kx. Okay, this is how it is. Is that clear?
Yes, sir.
Now, since my wave function is continuous, let us try to apply these conditions at first on x equal to a. So at applying continuity conditions of the continuity of wave function at x equal to a. So if at x equal to a, I'm talking about, so at x equal to a, and let us do it for the first case. Let us do it for the first even case. So first even case, what will happen? So even case x equal to a means, I think this will be equals to b cos hyperbolic ka must be equal to a e की power minus ka. And similarly for odd case, I'll write these equations, otherwise this will be a problem later on. So odd case, it will be, I think, b sine hyperbolic ka equals to a e की power minus k. Is that clear? So just
Yes,
applying the continuity conditions. So just applying the continuity condition, nothing else. Now, After this, you remember what we did in the previous instance that I was showing you. We used to integrate. So basically d square psi upon dx square plus 2m upon h ket square, and you had this uh, some v naught, and then we had some Dirac of x minus a plus Dirac of x plus a, and then we had 2m e upon h ket square. Okay. Now you should remember that this psi may even this psi can even be even and can even be odd. So, but if it is even, then it cannot be odd, and if it is odd, then it cannot be even. So, what I mean is my wave function has a definite parity. So either it can be even or it can be odd. So we will be considering two cases. One would be even bound states. Other case would be odd bound states. Okay, that is clear to you. So what I am doing first is I'm just considering my even cases. So what I would do is I would integrate it from because I've taken the continuity condition at A. So I would integrate this at particular expression. I would integrate this particular above differential equation from A minus epsilon to A plus epsilon. And if I integrate from A minus epsilon to A plus epsilon, it will give me d psi by dx from A minus epsilon to A plus epsilon. And then this particular term would become 0 because A minus epsilon, this particular term will become 0 because this is the Dirac delta function that is situated at x equal to minus A. So if I'm integrating from A minus epsilon to A plus epsilon, here this Dirac delta peak would come. So this is 0. Is that clear to you?
Yes, sir.
Okay. Now only you are left with this particular thing, and this particular thing will become 2m v naught upon h ket ka square. And this particular term will go to 0. That is absolutely fine. We have talked about it a lot many times. That if I integrate it from A minus epsilon to A plus epsilon, this will become psi A minus psi A, and this will become 0. Only thing that will give you a result is this Dirac delta function, because this Dirac delta function is located at x equals to A. So while integrating from A minus epsilon to A plus epsilon, it will filter out the value of psi, which is multiplied with this Dirac delta function. So here you will get psi of A. Okay, and I'm doing it for odd. I'm doing it for even. So I'll just write even. I will just write even. Is that clear to you? So
Yes, sir.
now this is the right hand derivative. This is the left hand derivative. So right hand derivative minus left hand derivative of the wave function psi even. So I'm writing psi dash. This is even. This is A plus epsilon minus psi dash even at A minus epsilon. And then you have plus 2m v naught upon h ket square. And then you have psi even A is equals to 0. Now, if I take the right hand derivative, what is right hand to A? Right hand to A is this value, that is k e ki power A e ki power minus kx. So if I just differentiate it, what would I get? I would simply get minus ka e ki power, I think minus ka, and to the left of this thing, I mean left to the left of A, my wave function is some cos hyperbolic. So what it will become? It will become some sine hyperbolic, because cos hyperbolic derivative is sine hyperbolic, and this will be kb sine hyperbolic ka. So with a negative sign overall. So this will be minus kb sine hyperbolic ka, and then you have some plus 2m v naught upon h ket ka square, and then what is psi even at A? You can just take any of one of them. So if I take this, then also there's no problem, because see, now you can do anything like psi at A can be written as psi of A minus epsilon, or you can write psi of A plus epsilon one in the same thing. So why to take a big term? Instead, I'll take just A e ki power minus k. So it will make my life a little bit easy. Okay, is that clear to you? So now what would I do? I would simply try to find some solutions out of this point. So just remember, this is a big question. It will never come in the examination, but overall, this will give you a lot amount of insights. That is why I'm doing it for you. And probably one or two question or करने के बाद we'll finish it off.
सर साई साई ए इवन लास्ट वाली टर्म आपने ये कैसे लिखी ए ई माइनस के ए?
साई देखो सुनो, साई इवन जो है आपका, there are two psi even at A can be written as psi even A minus epsilon. So I can write this way,
Right.
or I can
Yes,
write
sir.
this way. But see,
So okay.
Okay, so easier thing would be to do this, because otherwise this will create this cos hyperbolic come here, this will become sine hyperbolic, and probably things will become difficult for me. So what I did, I
Okay,
was
sir.
just seeing the symmetry of e की power minus k. Here also e की power minus k is there, and here also e की power minus ka would come. So overall, there's a
Yes, sir.
chance to simplify it. That is why I've done this, because you already know that your wave function is continuous. So whether you write psi of a, whether you write psi of a minus epsilon or psi a plus epsilon, they are one and the same. Is that clear? So we are cleverly
Yes.
using the continuity conditions, because otherwise, probably things may not turn up the way we want. Okay. So overall, I think I should just use these two things up and just assimilate them in one. So I will do it like this. A, I think this will become a constant Taylor's method 2m v naught upon h cat square minus, I think 1 should come. And then I will take e की power minus ka here. And it is equals to take that side, that will become k. Uh, there was no k here.
Yes, sir. There was no K here.
No k here. No? So what I would do is, chalo k common le lete hain. So here there will be a k. Okay, is that clear? And this will be
Yes.
kb sine hyperbolic ka. K gets cancelled. So overall, this particular expression reduces to I think solving this particular. See, let us see what can we do. So I'll write this equation as. So I'll write this equation as this. Equation number 3. This is my equation number 3. Okay. Now what would I do? If I apply the same thing on the odd case. So if I integrate the Schrodinger equation involving the double Dirac delta function, so involving the double Dirac delta function for the odd case. For the odd case. So if I just take an odd case, what would be it? I think it would be like d square psi upon dx square. Again, the same thing, plus 2m upon h ket ka square. You have this v naught, you have Dirac of x minus a, then you have Dirac of x plus a. Instead of all these things, we are using now psi odd. So here it will be psi odd. And then there will be some e psi odd. Okay, now if you integrate it from a minus epsilon to a plus epsilon, so if I integrate it from a minus epsilon to a plus epsilon, what I will get? I think I will get some right-hand derivative of the odd wave function. I don't think this needs an explanation now, right now. We've done it quite many times. Minus left-hand derivative of the odd wave function at a plus 2mv naught upon h ket square. And now instead of psi odd, you can write psi odd at a. Is that clear? This will become 0. I think इतना तो चलेगा ना, जल्दी से लिखना, otherwise.
Yes, sir. Yes.
Okay. Now psi odd at a plus epsilon. Let us go back and see. So psi odd at a plus epsilon. So this is simply this. This would be like minus ka e की power minus ka. So again it will be minus ka e की power minus ka and minus psi odd at a minus epsilon. Derivative, sorry. The derivative of psi odd at a minus epsilon. So derivative of psi odd at a minus epsilon. So this is sine hyperbolic x. Sine hyperbolic x when differentiated will give you cos hyperbolic x. Is that clear? So sine hyperbolic x when differentiated gives you cos hyperbolic x. So this will be minus of k b cos hyperbolic ka. I don't think there is a problem till now. And then you have this plus 2mv naught upon h ket square, and you can simply write it as e की power minus ka. And there would be some term also. There would be, I think, a also here.
Yes, sir.
Okay. So overall, if I just try to assimilate, I mean, put all these sums together, what I would get, I think, if I take ka common, then it will be, I think, 2mv naught upon. And instead of, I think last time we had sine hyperbolic, and
Yes,
this
sir.
time we'll have a
This.
cos hyperbolic. Instead of all those things, we'll have a cos hyperbolic. So this will get cancelled. Overall, you are with the term called as So this is how it is. So you have this term A. This is your equation number 4. So this is your equation number 4. Is that clear? So what we can do is probably we can remove this term by dividing 3 by 4. So divide 3 by 4 or 4 by 3, whatever suits you. So if I divide 4 by 3, 3 by 4, sorry, what I would get on the right hand side, I would get 10 hyperbolic Ka. And on the left hand side, you
1.
will, not 1.
Yes, sir. 1.
Okay. On the left hand side, okay, नहीं, but इसमें अपन दो गलतियां कर रहे हैं ना. We are dividing odd by even, so that will be a wrong thing to do. एक काम करो, जाओ, एक काम करो. Here we are dividing odd even by odd. नहीं नहीं नहीं, वो अलग
Yes, sir.
सोल्यूशन है. ये this is a solution for, एक मिनट को, this is a solution for, यहाँ लिख देते हैं नहीं तो कंफ्यूजन होगा. This solution for odd wave function. Okay, this is the solution for even wave function, right? And एक मिनट को, this is a solution for even wave function. और कुछ आया था क्या even के लिए? अच्छा ये रहा. This is the solution for even. So this is my even solution and this is my odd solution. Okay. So if even solution continuity, this derives its inspiration from even case. So similarly, I think I should divide, in whatever I should do uniformly, right? Because this is a solution for odd case. And the fourth one that we obtained is from odd case. So what I would do is I would prefer dividing 3 by 1. So I would prefer dividing 3 by 1 because 3 is an even case and this is an even case. So I'll divide 3 by 1. Is that clear?
Yes, sir. Yes, sir.
है ना, नहीं तो वो गलत हो जाएगा मैथमेटिकली. अब दो अलग अलग चीजें डिवाइड करो. सो डिवाइड 3 by 1. So what was your 3? 3 right hand side was, I think, b sine hyperbolic k a, and here you had b cos hyperbolic k a. So you just divide these two things up, so you will get 10 hyperbolic k a. So this will give you 10 hyperbolic ka is equals to, there was, is I think, एक मिनट देख ही लेते हैं इसको, otherwise
B.
a e की पावर माइनस के a जब डिवाइड हो जाएगा, so what will it give? b divides by b gives you 1. I think this will give you alone this entire term. So this will be like 2m v naught k h cat square minus 1. Is that clear? So if I divide 3 by 1, so if I divide 3 by 1, I will get this. Is that clear? देखो 3 पे क्या था आपका?
3 by 1.
ये रहा 3.
अच्छा अच्छा, ओके ओके, यस सर, यस सर,
क्योंकि
राइट.
देखो 3 इवन स्टेट बता रहा है एंड 1 भी इवन स्टेट के लिए ही दिस इज कंटिन्यूटी कंडीशन ऑफ साई फॉर इवन केस एंड दिस इज व्हाट वी हैव ऑब्टेन्ड फ्रॉम इंटीग्रेटिंग. ठीक है, इसलिए मैं ऐसा कर रहा हूं, अदरवाइज थिंग्स विल बिकम डिफिकल्ट. ठीक है, तो पहले इवन केस पकड़ लेते हैं. नाउ व्हाट डज इट मीन? इट मींस इवन बाउंड स्टेट्स, can be found by solving 5. Is that so? अगर 5 के जितने नंबर ऑफ सॉल्यूशंस आएंगे, जितने केस आएंगे 5 के लिए, उतने तो सॉल्यूशंस होंगे. आर यू गेटिंग माय पॉइंट? आई एम सेइंग,
राइट.
जब 3 को 1 से डिवाइड कर रहे हो, इफ यू आर डिवाइडिंग 3 by 1, यू आर गेटिंग some equation again in k. So if I solve this equation in k, and if this solution in k gives me, let's say, 5 values, then I would say there are 5 solutions. So there are 5 bounds, even bound state. Is that clear? तो वही गलती हो रही थी, हम 3 by 4 कर रहे थे, 3 by 1 करना है. Because see,
यस सर, यस.
यहाँ this is odd ना, so थोड़ा सा ध्यान रखना पड़ेगा. Okay, is that clear to you? So now let us try to find how many number of even bound states are possible, and that depends upon this. So अभी हम लोगों ने ग्राफ बनाया था sin hyperbolic का. Now try to make a graph of tan hyperbolic. So I'm just telling you right now, इसको मैं तुम्हें अलग से बनवाना सिखा दूंगा. So tan hyperbolic का ग्राफ ऐसा होता है. So tan hyperbolic as x tends to infinity, मैं you can verify it on your own self. बाकी हम लोग करेंगे, ऐसी बात नहीं है. tan hyperbolic x This is 1 and this is minus. And if you want to make a graph of tan hyperbolic x, it looks like this. It will start increasing and it will try to saturate. So it will saturate towards minus 1 as x tends to minus infinity. And it will try to saturate towards x equal to y equal to 1 as x tends to. Is that clear?
Yes,
This
sir.
is how your tan hyperbolic x or tan hyperbolic x look like. Okay, this graph is your homework. I will take a class probably on curve sketching also, so that that does not disturb you. Okay, so अभी बहुत randomly topics चल रहे हैं, but this is how things can be done. ठीक है, so this is how your tan hyperbolic x look like. So our energy is positive, so we'll only consider the case of positive side. So this is what I'm trying to do. एक काम करते हैं, थोड़े से कुछ substitutions लेके इसको easy कर देते हैं. Let us make it slightly easy. So I'm making my equation easy by certain substitution. Let's say if I take my Ka as, let's say, y. If I take my Ka as y. Okay, and so this will become tan hyperbolic y is equals to, एक काम करो ना. So Ka ले लिया ना, तो you just multiply here by a and here also multiply with a. So this will become some constant 2ma v naught h cat square will become some constant. Let us say it gamma, and then you have y. Is that clear? Here gamma is equals to what? It is a constant which is given by 2ma v naught upon h cat. Is that clear?
h cat square k.
देखो क्या किया, जस्ट a से मल्टीप्लाई कर दो इसको and a से डिवाइड कर दो. So this ka will become y and this entire thing is a constant. 2
Yes, sir. Got it.
2ma v naught. ठीक है. So this, but these two graphs needs to be seen. So well, I have already taught you that this graph tan hyperbolic y for all y greater than 0. Why I am considering only y greater than 0? Because I am only considering the I already know now this k is what? 2me modulus upon h cat square, isn't it?
Yes,
sorry,
sir.
root over 2me. So I'm considering the positive side. So this is 1. So this is how I'll make my tan hyperbolic here. Is that clear? Now, if I want to draw this graph, this is gamma upon y. So at y equals to gamma. So if my y is gamma, and don't get confused, this y is your, I should have taken it x here. So x ले लो. चलो कोई बात नहीं. You understood है ना, ये चीज समझ में आ रही है? It should have.
Yes, sir. Yes.
तो ठीक है, y चल रहा है. So at y equals to gamma, gamma upon gamma, this will become 1. So this is 0. So at y equals to gamma, this is 0. Is that clear? Now, as y tends to 0, this will become infinite. It will start from infinity. The graph will start from infinity. And the first derivative, so you have written the graph of you have drawn the graph of tan hyperbolic y. This is your tan hyperbolic y. And this is the graph of, what I'm drawing is now graph of gamma upon y. So at y equal to gamma, this is 0. As y tends to 0, this will tend to infinity. Infinity minus 1 is again infinity. And if you differentiate it, it will become minus gamma upon y square. So it will be negative, that is, it is decreasing. So it is a decreasing graph from infinity to. So how many number of solution can you expect? You can expect only one solution. And this one solution corresponds to one even bound state. Is that clear to you?
Yes, sir.
Okay. Another thing that you can see is, let's say this point is your y naught. So let's say this is your point y naught where your intersection came. Is that clear? Is that clear now? ये चीज समझ में आ रही है?
हाँ जी, sir.
Okay. Now we already know two things. The first thing that we know is, that this y naught, if I write tan hyperbolic y naught, this tan hyperbolic y naught is less than 1, because this is your 1. So tan hyperbolic y naught is less than. Is that clear to you?
Yes, sir.
Okay. So tan hyperbolic y naught is less than 1. What does it imply? It implies your gamma upon y naught minus 1 should also be less than 1. it implies that your y naught, if I write, it will be, I think, 2.
Greater than gamma.
I think this will be y naught should be greater than 2 times gamma. Is that clear? No,
Yes, sir.
This is, I think, 2
2y naught.
Gamma by 2. So y naught will be greater than gamma by 2. Is that clear? And another thing that you can see is y naught is less than gamma. So I can write that my y naught lies between gamma by 2 and, gamma by 2 and gamma. Is that clear? देखो, 10 y naught is less than 1. It implies y by gamma, gamma by y naught minus 1 is less than 1. It implies y naught should be greater than y by 2. And similarly, y naught should be less than gamma. That is clear. Y naught is less than gamma. Okay, is that clear?
Yes, sir.
And if I just
Yes, sir.
square it up, what would I get? If I just square it up, I'll get y naught ka square, gamma square, and then I will get gamma square by 4. Is that clear?
Yes.
And if I want to write some expression, so y is what? So this is k square a square. So this is k square. A square is less than, I think this is gamma square. And gamma square is what? Gamma square would be 4 m square a square v naught square h cat ki power 4. And then this will be, I think, if I'm not wrong, it will be m square a square v naught square upon gamma ki power 4, because there is a 4 here. Now, we already know that your k square is nothing but minus 2me upon h cat square, if you remember.
Yes, sir.
है ना? So your k square is minus 2me. So if I want to, and this is even, we are discussing. So I'll write minus 2me even upon h cat ka square lies between all these things. And if I want to extract what will be my even energy and what will be the bounds of even energy, I can find that. So my even energy bounds, this h cat square, this will become h cat square. It will become h cat square. And then I have to divide minus 2m. So if I divide minus 2m, this particular thing will come here. So this will be minus 2m a square v naught ka square. And here it will become, I think, m a square v naught ka square. Negative. Where this a is coming, I don't know. Acha, a bhi to cut hi jayega na. This is a will get cancelled. So a will also get cancelled. So my energy even would lie between minus 2m v naught square upon h cat square to minus m v naught square upon 2x. Is that clear to you?
Yes, sir.
So this is range of even energy. So I'll meet you in the next lecture.